Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as circular motion. Right? We are going to do this in terms of circular motion. First let's find out what do we understand by uniform circular motion. What do we understand by uniform circular motion? Now uniform circular motion is defined as the motion of a particle along the circumference of the circle with a constant speed. Suppose if a particle is moving along the circumference of a circle, it's moving on this line and it is moving with constant speed, then that is what is called as UCM. Henceforth, I will be referring to uniform circular motion as UCM. Okay, so how do I define this? Uniform circular motion is defined as the motion of a particle along the circumference of a circle with constant speed. Okay. Now, if a body is going to move along the circumference of a circle, then it is going to cover some angle. Let's see this. You have a body. Let's assume that this is the center. OA is the initial, or OP is the initial point where the body is. Let's assume that in time interval T, the body covers an angle of say theta and moves from P to Q. Right? Now, this angle that is covered at the center is called as angular displacement. So what is angular displacement? Angular displacement of a particle in a given time is defined as the angle traced by the radius vector in a given time. This radius vector moves from OP to OQ. The angle that it covers would be called as angular displacement. So angular displacement definition. Angular displacement is defined. Angular displacement of a particle is defined as angular displacement of a particle in a given time. Is defined as the angle traced by the radius vector So angular displacement of a particle is defined in a given time is defined as the angle traced by the radius vector in that given time. Right? What will be the SI unit of it? The SI unit of it, since it is angle, it is measured in radians. Fine. So how do I define angular displacement? Angular displacement is the angle in radians. Right? Therefore, I can say angle in radians. Now we've said in 11th standard we had learned that S is equal to R theta. Length of the arc is radius into theta in radians. So this can be written as arc upon radius. Why? Because S is equal to R theta. Length of the arc is radius of the circle into the angle. Right? So in which case I will therefore say that angle in radian theta is equal to nothing but length of the arc PA or PQ upon radius R. So this will be S upon R. That is what is angular displacement. Fine. Next, what do we understand by angular velocity? angular velocity is defined as the rate of change of angular displacement. Angular velocity is defined as the rate of change of angular displacement. What does that mean, guys? It means how much angular displacement is covered in unit time. Right? We get this thing here. It is represented as omega. So angular displacement, angular velocity is change in angular displacement per unit time. So omega is d theta by dt. It is defined as the angle traced by the radius vector per unit time. Fine, do we understand this? That is what is angular velocity, right? Now in UCM angular velocity, this is how you will define this. Okay. Next, let's move on to. So, what will be the SI unit of this? The SI unit will be radians per second, right? That is your angular velocity. Next, angular acceleration. Angular acceleration. How do I define angular acceleration? Angular acceleration is defined as the rate of change of angular velocity. Definition: it is the rate of change of angular velocity. Right? So, alpha is the change in velocity with respect to time. So, final velocity minus initial velocity upon time. Right? Do we get this thing here? Or I could also say that angular acceleration alpha is the change in angular velocity with respect to time. Fine, do we get this thing here? Now, what will be the SI units of this? The SI unit will be nothing but radians per second square. Fine, do we get this thing here? Now, angular acceleration, is it a vector quantity or a scalar quantity? It is a vector quantity. Right? It is a vector quantity and it is because angular velocity is also a vector quantity. Fine, do we get this thing here? Next, let's find out the relation between linear velocity and angular velocity. Right, let's find out the relationship between linear velocity and angular velocity. Let us consider this. I have a circle. Right, let's assume that O is the center of the circle, OA is my radius vector. Let's assume that the radius vector and its length is r. Let us assume that the radius vector moves from OA to OB and covers a small angle d theta, right? Such that the arc that it makes is delta s. That's my length of the arc, right? So we'll say that let us consider a particle performing UCM, right? Now, let us also assume that in time delta t, the particle moves from A to B and covers an angle of delta theta and an arc of delta s. Fine, do we get this thing here? Now, since delta t is an extremely small time interval, now we know that linear velocity is linear distance upon time, right? Since delta s is very small, it is approximately a straight line. Therefore, I can say that linear velocity V is limit of delta t tends to 0 delta S upon delta T. Velocity is displacement upon time. I'm using the simple logic, right? But we also know that delta theta is nothing but delta S upon R, right? So in that case, I can say that delta S is equal to R delta theta. I can substitute this in the equation of linear velocity. Therefore, I can say linear velocity is limit of delta t tends to 0, R delta theta upon delta t. Whatever is constant comes outside the limit. So this is R limit of delta t tends to 0, delta theta by delta t. But change in displacement upon, that is change in displacement upon time, angular displacement upon time is nothing but angular velocity, but limit of delta t tends to 0, delta theta by delta t is omega. Therefore, I'll get V is equal to R omega. Fine, we get this thing here. So this is the relationship between linear velocity and angular velocity. If they ask you to express this in vector form, V vector is equal to R vector cross omega vector. Fine. Okay, this is going to be omega vector cross R vector. Fine, do we get this thing here? So that is going to be my relationship between linear velocity and angular velocity. Fine, do we get this thing here? Next, let us find out the relationship between linear acceleration and angular acceleration. Acceleration and angular acceleration. So in which case I can say that, let us assume that a body is in UCM. Let a body be in UCM, right? Now let us assume that the linear speed is v and the tangential acceleration is at. See, when a body is in UCM, when I release the body, it will always move in tangential direction. So you will say let v be the linear speed and at be the tangential acceleration. Right? Now I can say that linear acceleration is nothing but change in linear velocity upon time, but we have just derived that V is equal to R omega. Therefore, I can say that AT is equal to d by dt of R omega. R is a constant, comes outside the derivative sign, so d by dt of omega. But d by dt of omega, rate of change of angular velocity. Rate of change of angular velocity is nothing but angular acceleration. I can say but d omega by dt is nothing but alpha. Therefore, I can say AT, tangential acceleration, is equal to R alpha. Fine, did we get this thing here? Next, let us find out the period and the frequency of revolution. Let's try to find out the period of revolution of a UCM. Now, first of all, what do you understand by period of revolution of UCM? It is the time taken by a particle performing UCM to complete one revolution. Definition: it is the time taken by a particle performing It is the time taken by a particle performing UCM to complete one revolution. Right? Now let's try to understand this. Now guys, let's assume that a body is moving in UCM anti-clockwise. Let's assume it starts from point A. It moves around the circle and comes back to point A. Then what is the distance covered by the body in one revolution? The distance covered by the body in one revolution is nothing but the circumference, and circumference is nothing but 2 pi r. This is the distance covered. Let us assume that let linear velocity be v. Now we know that velocity is equal to distance upon time. Therefore I can say that time is nothing but distance upon velocity. So distance is circumference upon velocity. So period t is nothing but 2 pi r upon v. So that is your time period that will be taken for one revolution. But we know that v is equal to r omega. I can substitute the value of v as r omega. Therefore I can say t is equal to 2 pi r upon r omega. Therefore I can say t is equal to 2 pi upon omega. Right? Therefore the time period of revolution is 2 pi divided by angular velocity. Right? Next, let us find out the frequency of revolution. Right? Now what is frequency? Definition: it is defined as the number of revolutions performed per unit time. Frequency of revolution, definition: it is number of revolutions per unit time. That is what is my frequency of revolution. So thus I can say that frequency n is 1 upon t, but t is nothing but 2 pi upon omega. Therefore I can say n is 1 upon 2 pi upon omega. Denominator becomes numerator. So n will be nothing but omega upon 2 pi. Fine. Next, let us find out centripetal acceleration. Let us try to find out centripetal acceleration. Centripetal acceleration. Right? Now, let's assume that a body is performing UCM. Right? Let's assume that O is the center, OA is my radius vector, right? Let's assume that the body moves from A to B. So in which case I can say that, let us assume that the angle that it covers is delta theta, and right? Now, as the body is moving in a UCM, suppose if I release the body at point A, in which direction will it move? It will move in tangential direction. This is the direction that it will move in. If it is going to move in this direction, with what speed is it going to move? It is going to move with a speed of linear velocity. So it will move in the direction of AT with a speed of linear velocity v. Suppose if I release the body at point B, in which direction will it move? It will move in the direction of BQ. Right? It is going to move in the direction of BQ. With what speed is it going to move? It is going to move with the linear, it is going to move with the speed of linear velocity. So let's just write this down. Consider a particle A, consider particle A moves to particle B, position B. Right? a particle moves from A to B in time interval. Consider a particle A moves to position B in time t. Let's consider that the time is very small. Let's assume that it moves in time delta t, right? So in that case, AP vector and BQ vector denote the velocity of particle at A and B. Therefore, I can say that AP vector and BQ vector denote the velocities of the particle at point A and B, right? Right? Now, in that case, I can say that the linear speed of the body is constant. The linear speed of body is constant. The linear speed of the body is going to be magnitude of AP vector, which is equal to magnitude of BQ vector is equal to V. Let us assume that the linear speed is equal to V. Now I'm going to just draw that separately here, right? Since these are vectors, I can move them as and when I want or in the position I want. Let us assume that this was my BQ vector, right? Let us assume that I pick up AP vector and I place it at BQ vector, at the starting point of BQ vector, right? So let us assume that, let's call this as BR. Let BR vector be equal to AP vector. That means it is going to be the same in magnitude and direction. Therefore, AP vector now can be represented by BR vector, right? Now, in that case, I can now complete this triangle, right? If I complete the triangle, then I can say that in triangle BQR, I can say that BR vector plus RQ vector is equal to BQ vector by triangle law. I can say that BR vector plus RQ vector is equal to BQ vector by triangle law. Triangle law of vector says this. So in that case, I can therefore say that RQ vector is equal to BQ vector minus BR vector, right? Now, I can say that but BR vector is equal to AP vector. BR vector is equal to AP vector. Therefore, I can say that RQ vector is equal to BQ vector minus AP vector. But what is BQ? BQ is nothing but the velocity of the particle at B. So I can say that RQ vector is nothing but the velocity of particle at B minus velocity of particle at A. So that means RQ is nothing but the difference between the velocities. So therefore I can say that RQ vector is nothing but the difference in the velocity. There is going to be a small change in the velocity. It is the difference in the velocity. Now, so it is the difference in velocity in some time interval dt. Now let us assume that acceleration. What is acceleration? Acceleration is nothing but change in velocity upon time. Change in velocity upon time, right? Therefore I can say acceleration is limit of delta t tends to 0, change in velocity delta v upon delta t. That is what is acceleration, right? Now in that case I can also say that by geometry, guys, by geometry I can say that angle AOB is going to be equal to angle RBQ, right? How do I get this by geometry? By using similarity. You're not going to do that. You have to only know that both the angles are going to be same using similarity. So both of them are going to be delta theta, right? That means, guys, can you see this figure? This angle therefore is going to be delta theta, right? Now this is theta, and I can say that let's assume that this we know is velocity. So I can use the formula of geometry. S is equal to r theta. Length of the arc is radius into angle. So I can therefore say that delta theta is nothing but length of the arc is rq in that figure and radius is v, right? So I can therefore say that this is nothing but rq we found out is delta v upon v. Hence I can say that delta v is v into delta theta. Fine, do we get this thing clear? Now I could substitute this in the formula of acceleration. I can therefore say that acceleration is limit of delta t tends to 0. Instead of delta v, I can say that v into delta theta upon delta t. Whatever is constant comes out. So I'll get v limit of delta t tends to 0, delta theta by delta t, right? But delta theta by delta t, change in displacement upon time, is nothing but angular velocity. So therefore I'll get A is v into omega, where because limit of delta t tends to 0, delta theta by delta t is nothing but omega. That's the reason. Okay. So once you have this, that is your relationship between linear acceleration and angular velocity. But I could also say v is equal to r omega. Therefore I can say that A could also be written as r omega into omega. So A is equal to r omega square, right? But omega, we could write this way, or we could also say v is equal to r omega. Okay. I can say that again. A is equal to v omega. Omega can be written as v by r. Also, omega is nothing but v by r. If I substitute this here, I'll get A is v into v by r. So A is equal to v square by r. Right? So these are your various relationships that you can have for centripetal acceleration. Right? This is how you find out centripetal acceleration. Next, let's see the next thing. Let us find out what are the different types of forces that act on a body when a body is in UCM. First is centripetal force. Right? When a body is in UCM, right? When a body is moving in UCM, guys, try to take a string with a stone attached and try to move it. You will feel that there is some pressure on the hand where you are moving it. So that means there is some inward force that is acting on the body, right? Suppose this, and suppose if I have a body of mass m here, then we know that force is equal to ma. A we just found out is v square by r. So you would have an inward force of mv square by r acting on you. And this force is called as centripetal force. So what is centripetal force? Centripetal force is a force that is directed inwards when a body is moving in UCM. So if a body is moving in UCM, the force that is directed inward is called as centripetal force. Fine. Next, centrifugal force. Now if I apply Newton's third law to this, or before that, if there is a centripetal force and the centripetal force is acting inwards, that means the body, instead of moving in UCM, should move inwards towards the center. But the body does not move inwards towards the center, it keeps rotating in that UCM. That means there has to be some outward force acting on it. This outward force that acts on the body, which keeps the body moving in UCM, is called as centrifugal force. So what is centrifugal force? Centrifugal force is a pseudo force. Why do I call it as a pseudo force? Because it is not a force generated on its own, it is a reaction force to the centripetal force. Okay? So when a body is moving in UCM, The reaction force to the centripetal force is called as centrifugal force. It is a force which is directed outwards. Fine, do we understand this? So centrifugal force is an outward force that is acting on the body. Right, do we get this thing clear? So once you have this, next let's try to see roads. What do we understand by banking of roads, and why do I need to bank roads? Banking of roads. Right? What do we understand by banking of roads? Now, see, when a car or any vehicle is taking a turn at high speed along a curved road, the car skids. Why? Because at that point of time, when a body is moving on a curved road, at very high velocity, the centrifugal force becomes more than the centripetal force. Therefore, the car skids outward. Right? Now, this skidding of the car is going to cause wear and tear of the vehicle as well as the tire. Right? When the car is moving on a curved road at very high velocity, the frictional forces which exist between the tire and the road are not sufficient. They do not provide sufficient grip, and as a result of which the one end of the car skids outward. Now I don't want that to happen. To prevent that, you have this technique. You can prevent that from happening by using a technique called as banking of roads. Right? Now, every vehicle has a maximum speed at which it can move on a curved road, right? If it does not move at that speed, if it moves at a speed higher than that, then the car would skid. In order to prevent that from happening, you have banking of roads. So what is banking of roads? Banking of roads, in order to do that, now if I show you a cross section of the road, right? This was a top view. Suppose if I show you a cross section of the road, ideally the road should be this way and this should be the vehicle that should be on the road. The vehicle is moving inward, right, on the road. Now, as a result of which the vehicle could skid. So instead of keeping the road straight, what am I going to do? I'm going to elevate one end of the road. Now, as it tries to skid, since one end of the road is elevated, that will provide the necessary force inward. So as a result of which my centripetal force will increase, and now the centripetal and centrifugal force will be equal and the car will not skid. Right? So what is banking of road? Banking of road is nothing but the angle made by the road surface with the horizontal. That is called as angle of banking. What is banking of road? It is raising one end of road with respect to the other end of the road. It is raising one end of the road with respect to other end of the road. Fine, do we get this thing clear? So, do we understand what is banking of road? In that case, what is angle of banking? Angle of banking is the angle made by the road surface with the horizontal. Is called as angle of banking. In this case, if I am raising the road this much, then this would be called as angle of banking. Now, how does angle of banking help, and why do you have certain roads that have certain speed limits, and why should you follow them? Right? Let's try to derive an expression for angle of banking. Right? Now, I'm going to show you the cross-section view. Let's assume this is the road. Let's assume that it is properly banked at an angle of theta. Right? Let us assume that you have car moving on this road. Right? This is the car that is moving on the road. Now let us try to find out what are the forces that are acting on the car. The forces that are acting on the car, obviously one of them is going to be the force downwards, that is the weight of the car mg. Now to this particular force, by Newton's third law, there has to be a reaction force. So this is going to be the reaction force that is going to be acting vertically upwards, otherwise the car would be sinking in the road. The fact that it is not sinking, that means there is a reaction force. Now since the reaction force is a vector, that means it can be resolved into two components. It can be resolved into two components, one along horizontal and one along vertical. Right? The horizontal, if this angle is theta, the horizontal component provides the counterbalance force for the force that is acting downwards, and the vertical component, this actually here it looks this way, the diagram has been turned. So here if I call this is going to be my horizontal component. Horizontal component, actually it should be r cos theta, but your diagram is turned, that's the reason why the vertical component is appearing horizontal this way. So we will refer to this as horizontal. The horizontal component provides the necessary centripetal force, and the vertical component counterbalances the weight of the car. Fine? And that is the reason why the car can smoothly move on the road. Fine, do we get this thing here? So let us consider a vehicle of mass m moving on a curved road of radius r, banked at an angle of theta. Right? Now in that case, while taking a turn, what are the forces that are going to act on the car? While taking a turn, the forces that are going to act on the car is the weight acting vertically downwards. While taking a turn, forces acting on the car will be one, weight mg acting vertically downwards, the weight obviously is going to act vertically downwards, and the normal reaction force between the vehicle and the road, and the normal reaction force R between the vehicle and the road. Right? Now, this normal reaction force can be resolved into two components. The normal reaction force can be resolved into two directions. Right? The vertical component is going to be r cos theta. The vertical component is going to be r cos theta, and the horizontal component is going to be r sin theta. Right? That means from the figure it is very clear that r cos theta is balanced by the weight mg. From figure, r cos theta is balanced by the weight of the car mg. Therefore, I can say that r cos theta has to be equal to mg. Right? Similarly, the horizontal curve is the horizontal component r sin theta is acting inward. That means it is going to provide the necessary centripetal force. I can say that the horizontal component r sin theta is directed towards center, right, and provides the necessary centripetal force. Therefore, I can say that r sin theta is equal to mv square by r. Right? Let's divide the two equations. Let's call this as equation 1. Let's call this as equation 2. Divide equation 1 and 2. If I divide equation 1 and 2, I'll get r sin theta upon r cos theta is nothing but mv square by r divided by mg. R and R gets cancelled. Sin theta upon cos theta is tan theta. M and M gets cancelled. It's v square by rg. So the angle of banking theta should be equal to tan inverse of v square by rg. So in order to prevent skidding of the car, the angle at which a road should be banked is given by the formula tan inverse of v square by rg. Now what is the maximum speed with which a car can be safely driven on the road? I can say, if from this equation I can say v square is equal to rg tan theta. Therefore v is square root of rg tan theta. That's the maximum speed with which a car can be safely driven on the road without skidding. Fine, do we understand this? So do we understand an expression for angle of banking? Right? We'll stop this here for the day. Thank you very much.